That I want you guys to know is what makes a gas ideal and how we're going to be starting for an ideal gas. Now, first of all, we're talking about gases, right? And gases are free to move. It's not like solids. Solids are packed. I break that arrangement. We get to liquids. Liquids are a little more free to move. There's intermolecular forces between them. That's the very last set of lectures we're going to have after the exam. And then we get to a gas state, which is free to move. And in order for me to deal with gases, gases have to be contained. So when I represent gases, guys, I'm going to have a box, and then you got all these particles moving within the gas. Within the box. So I have a container because gases must be contained. And we're going to be studying ideal gases. So the case that we're going to be looking for is for an ideal gas case. We're just going to try to represent, situations that are, they're real, but we're not dealing with the equations that are for real gases. If you want to know those equations, you could talk to me individually. I'll give you guys some taste of equations that represent real gases versus ideal gas situations. But how we're going to be studying these gases, guys, is through 4 different variables: volume, pressure, temperature, and the moles. And I want to first make sure we understand what these variables are about. The first variable, guys, is about volume. It's given by the symbol V. And this volume, according to our very first assumption of what makes it ideal, the volume that we're dealing with, guys, is going to be the volume of the container. I'm not going to write down the first assumption, but I want to speak about the first assumption. The first assumption, guys, tells me that the volume of the container is so much larger than the volume of the gas itself. Okay, I'll write it down. Right, so we have first assumption. It says that the volume of the container is going to be much, much larger than the volume of the gas itself. That's what makes it ideal with that first assumption. So when you deal with this V, that's going to be the space available for the box or the container of the gas. So we don't have to worry about the amount of volume that the gas takes. Guys, let's pretend we are the gas particles. We're moving around, right? If I ask you how much space is available for your movement, wouldn't that be the volume of the container minus the amount of space that you take, each of us take individually? That would be for a real condition. For an ideal case, we're going to assume that the volume of the container is so much larger than the amount of space that we take that we could consider the V as just the volume of the container. So for example, if you take dust particles in the air, and I ask you, what's the volume available to the dust particles? You don't have to consider the volume of the dust particle itself. You could just say, oh, it's the volume of the empty room, because dust particles don't take too much room in that space, right? Do you see what I mean? And so the very first assumption is only there for us to realize that, okay, look, when I deal with the volume, I have to deal with the volume of the container. I don't have to worry about how much space the gases themselves take. So what's my volume as a gas? I'm not worrying about that if it's an ideal situation. Are we clear on this? And so the smaller the gases are, the more ideal it is for our study. And that's a question I like conceptually. A lot of times I'll bring that question. So the smaller the gas, the more ideal the gases are going to become. Just so I could test to see if you guys are okay with the first assumption. So if I give you guys cases like N2, oxygen 2, and I don't know, fluorine 2, which one is the smallest case here, guys? The size of the atoms as you move in this direction becomes what, guys? Becomes smaller. Okay, so because fluorine is smaller, I would say this is more ideal, right, for studying, more ideal. So smaller the gas, the more ideal it becomes for studying. So the size does make a difference in terms of, is it ideal for my studying or not? That's the first assumption. Why am I making these assumptions? So we could make a little more sense out of the variables before we get into the equation. And these are the variables we're going to use to study how the gases behave. It's through tweaking the volume, pressure, temperature, but let's understand the variables first. Are we okay with the first assumption? Go ahead, Asher.
I thought like the more we went to the right, it got small. Or because
No, if you go to the right, it gets smaller, right? Because if you're on the same, we'll talk about that, Arshad, individually. But I'll give you those patterns. If you go back to the lecture notes on the patterns for atomic size, as you move from left to right, it gets smaller. You got to know that. Why? Because what dominates is the Z effective, the number of protons. Will pull the electrons close. Okay. But let's get to the ideal gas law problem. So we'll talk more individually about those patterns. We should have started that for the exam. So that was the first assumption. And so when it comes to the V is what? Is the volume of the container. What about the pressure, the P here? And what is pressure, guys? Now, I'm going to give you an equation. Pressure represents force over an area. You guys do not have to use this equation. This is only there for us to realize what pressure is all about. There's a whole course which studies pressure, starting with some introductory physics courses. So we're really not using this equation. This is only there so we can get the intuition of what P is. So P is about pressure, and pressure is defined as the amount of force the gases are going to exert on a given area. And we got units associated with it. So some of the units are atmospheres. We're going to see that. That's one of the common units we're going to use. Millimeters Hg, it's another unit for pressure we're going to use. Torr is a unit of pressure we're going to use. And if you ever want to go from one unit to another, I'll provide you with the equalities in our problem solving, so you don't have to worry about that. And you'll see within the problem solving that I am going to provide you with the equalities when it comes to pressure. There's units like Pascal, and Pascal is defined as newtons per meter squared. Newton represents a unit of force from Isaac Newton, right? Reminds me of a joke I was telling the other class yesterday. You guys want to hear another chemistry joke? I apologize beforehand for another chemistry joke. Anyways, Einstein, Pascal, and Newton decided to play hide and seek. A friend of mine told me this, and I was kind of laughing, and it was embarrassing. But let me tell you the joke. It's more of an educational joke. Einstein does the counting. He says, "Okay, I'll do the counting," and Newton and Pascal are trying to hide, and Pascal goes behind the curtain, and Newton doesn't know where to go, so he draws a little square, and he stands right in the middle of the square. So Einstein turns around and says, "Okay, I see you." He's like, No, you don't see me, you see Pascal." And I was laughing about that, and let me tell you why. I'm sorry for the chemistry joke, everybody's quiet. Newton over a square meter represents units of Pascal, which is pressure. Pascal formulated this, the formula of force over area representing pressure. Again, I apologize for the joke. A friend of mine knew I was going to laugh, and he was just like, everybody thought. All right, it's educational, so we don't have to laugh. So it's more like if I draw a square, and I'm Newton, and I stand in the middle of the square, and that's Newton, units of Newton, over meter squared, right? It's a little square, so there's an area. And so that's going to be force over area. Is it clear? Yeah. It's funny now, right? Is it funny? Okay, it doesn't matter if it's funny. Is it clear, guys? All right, so pressure is about force over area. And believe me, guys, let's say, just to have an idea about this, so let's say you got a person who's wearing regular shoes versus high heels, and they step on your toe. Same person. Which one is going to exert more pressure? High heel. All that force is going to go through a smaller area, right? And so when it comes to pressure, the reason I'm talking too much about this, pressure is going to be about the force that these gas particles are going to exert on the surface area of the container. This is the picture that I want you guys to have when you're considering the pressure due to gases. Gases are going to have pressure associated with it. Because there's going to be force associated with the gases, and there's going to be a surface area that holds them, and so that's going to tell us information about the pressure associated with the gases. So the reason I brought this up, so we can have the intuition of what pressure is, because we want to be able to see how gases behave through these variables, so we need to first understand these variables. And these are some of the units that we get for pressure. Another unit that comes to my mind is pounds per square inch, PSI. That's about pressure, right? You measure the tire pressure is in units of PSI. Pounds represents force divided by a square inch represents an area, so we're talking pressure. That's pressure, okay? Then we have the temperature, T. And when it comes to ideal gas laws, when we get to the problem solving, I'm going to emphasize this many times. When it comes to temperature, we got to use units of Kelvin for temperature. Or you get problems where they'll give you Celsius, but make sure you guys convert it to Kelvin when we do problem solving, because we got to make sure that the temperature units are in absolute units of temperature. Why? Because you can't have negative values for temperature in the equations we get, because if you have negative values, you might get something like negative volume or negative pressure. And that's not true. You either have volume or you either have space or you don't. Or you either have pressure or you don't, guys. So when it comes to temperature, we're going to have to make sure that it's absolute. And what does temperature tell us? What is the temperature going to tell us, right? Temperature, guys, is going to tell us about the movement of the particles. So if you go into the notes, I bring this up. This is called the kinetic theory of gases. And we're not going to do any problem solving for this, but I bring this up so we could build our intuition of what it means by temperature when we deal with ideal gas laws. And it relates the kinetic energy of the gases. And the kinetic energy of the gases is given by 1/2 mv squared. I could also write the kinetic energy of the gases in terms of, for a three-dimensional box, in terms of how it relates to temperature. And so we come down to this equation that shows that the average velocity of the particles relate to the temperature. This is about the kinetic theory of gases. The reason I brought this up is for you guys to realize that as the temperature goes up, so as far as our intuition should tell us about temperature, as the temperature goes up, what should happen to the particle movement on average? We should move faster. As the temperature goes down, what should happen to our movement? We should slow down. So when it comes to temperature, guys, the reason I have this slide in my notes is for you guys to realize that temperature is going to tell us about the average movement of the particles, so it explains that part. More specifically, if you guys want to read about that more, it's called the kinetic theory of the gases. It's only there for this class to introduce us to the fact that, as temperature goes up, there is more kinetic energy, and so the particles on average are going to be moving faster. So there goes temperature. And then we have the moles. What about the moles? The mole is going to represent the number of the particles we got eventually, right? And so it's these 4 variables that we're going to use to study ideal gases. And we have experiments that's going to study 2 variables at a time, guys. It's going to consider 2 variables at a time to see how the gases behave. And there's 4 different experiments that I want to bring to your attention. And it's through these experiments that we're going to come up with an expression eventually for our problem solving, the equations we get for our problem solving. First experiment, it's about Boyle's law. And I'll ask you, if I ever ask you what's Boyle's law, for Boyle's law, guys, we're going to be studying volume versus pressure. So if I ever ask you what's Boyle's law about, Boyle's law is going to study volume versus pressure. So I have it on the slide. Can you guys see? So first thing I want you guys to know about Boyle's law study is the fact that we're studying volume versus pressure, or pressure versus volume. And before we look at the experimental data, let me ask you, if I decrease the volume, just so we can kind of check our intuition for it. And by the way, when we study volume versus pressure, we're not varying moles and temperature. So for Boyle's law, I'm only choosing to study how, if I increase or decrease the volume, what happens to the pressure. Given that the moles and the temperature are not varying, they're constant. So nobody's going. So if we are the gas particles, none of us are going to go in and out of the room. And I'm not increasing the temperature or decreasing the temperature, so our average kinetic energy is the same. So what I care about, guys, is for you guys to realize this: as the volume goes down, what should happen to the pressure? By our intuition, it should go up. Guys, if we are the gas particles, and I maybe shrink the volume by half, there's less surface area, and we're going to collide with the same force, but there's less surface area, and so the pressure does what, guys? It goes up. Don't forget, pressure is about the force that we exert on a given area. So if there is less surface area, because the container shrinks, the volume is decreased, then I'm going to end up exerting more, more pressure. That same force is applied onto a small surface area, so it's narrowed down to a smaller surface area, and so the pressure goes up. This is what our intuition should tell us. But let's see what the experimental data is going to tell us. And what Boyles is going to do, guys, is going to formulate it. It's going to put it together into an expression. So if you take a look at the experimental data for the Boyles law, as the volume goes up, what should happen to the pressure? The pressure goes down. It goes according to our observation. But he wants to put this together into a formula, into an expression. And so he takes, for each experimental result, guys, he takes the volume and multiplies it by pressure. And every time he takes the volume for a given experimental result and multiplies it by pressure, he's getting more or less the same value associated with that. Let's check this. 12 times 1, 117.6 gives me this 141.1. By the way, there's a typo, this is 0.1. This times that gives me 140.6. This times that gives me 140.6. The point being is, every time, according to the Boyles law and his experimental data, he takes the volume, multiplies it by pressure, more or less, because it's not completely ideal, but more or less he's getting what, guys? He's getting a constant volume. More or less he's getting a constant volume. Okay? So what we get is P times V must be equal to a constant. That's what I want you guys to know about Boyle's law. And I'll bring this up. You're required to know this now. I could ask you, and in order for you to know this, you're going to have to refer to the notes. This is how I know who came to lecture, who did it. Right? So P times V is equal to a constant. That's Boyle's law. So if I ever ask you in a multiple choice, can you be able to identify which expression is the Boyle's law? First, you have to realize Boyle started gases through volume versus pressure, right? He took those two variables and he was tweaking those variables to see how they behave, given that the moles and temperature are not changing, and he realizes that P times V must be equal to a constant. And I can also express this as P1 V1 is equal to a P2 V2. And by the way, P times V is equal to a constant does explain this behavior, this inverse behavior between volume and pressure. Imagine, so just to make up numbers, right? If I have 2 times 2 is equal to a 4, and I change my pressure, so this is pressure, this is volume, and let's say we change the pressure to a 4, what must happen to the volume in order for me to multiply to be equal to the same number? It must decrease to a 1 in order for this to multiply to the same non-varying number, which we call a constant. And so it explains the behavior we see or expected from the beginning. If I shrink the size of the container, then the pressure must go up. Pressure has to do with the force we exert on a given area. Less surface area, so I'm exerting a little more force. Any questions about Boyle's law? Or what I want you guys to know about Boyle's law? So when it comes to Boyle's law, guys, I want you guys to know these expressions. It's worth remembering those expressions. So make sure you guys take a look at that. Okay, so that was Boyle's law. The next study is going to take volume versus temperature. And we have a name for that study, and that study, guys, is going to be called Charles' law. Just so you guys know, could realize how to navigate through the notes, right? So the next law there's 4 laws that I want you guys to be aware of. Boyle's law, then it's Charles' law, and what did Charles' law study? Did you guys copy it? Charles' law is going to study volume versus temperature. That's Charles' law. So according to Charles' law, I want to know how volume and temperature vary given that the pressure and the moles are not changing. So I'm going to now take 2 of the variables and tweak the temperature and see how the volume changes or tweak the volume and see how the temperature changes, so I could see how the gases behave. And so let me ask you, what happens if you decrease the temperature to a balloon? Let's say you take the balloon and put it in a cold, I don't know, in a refrigerator, or put it on outside under the cold weather. Is it gonna increase in size, or is it gonna decrease in size? It's gonna decrease in size. And it does that so it can maintain the pressure, the atmospheric pressure, and the pressure from inside must be maintained in this case. And let's say no gas is leaking, so the moles and the pressure are not changing. So if I decrease the temperature, and the reason we talked about kinetic theory is because decreasing temperature should give us a picture of the gases slowing down, because the gases are now slowing down, right? And there's going to be less force exerted onto the wall, so the size of the balloon is going to shrink, so it could maintain that force, because I'm not maintain the pressure. I didn't mean to say force. And so as the temperature goes down, my volume should do what? It should go up. Charles is going to check this fact in his experimental data. And in his experimental data, we see that as the volume goes up, this is the volume, by the way. It's all in our notes, guys, what I'm projecting here. For Charles' law, if you take a look at the data, as the volume goes up, what should happen to the temperature? Sorry, the volume is going up and the temperature is doing what? Is increasing. What the heck did I just do here? Erase that part. As the temperature goes down, we talked about this, the volume should be also decreasing. I'm glad to look at the experimental data. So the volume and temperature, according to the Charles study, is directly proportional. But what is it that I want you guys to get out of the study? The relationship he gets in an equation, guys. I want to make sure that we know the expression he gets. And so when he checks the experimental data, every time he takes the volume and divides it by the temperature, and notice that this is in Celsius, so he first changes the temperature to what, guys? Kelvin. You can't divide it by 0, by the way. It's infinity. So every time he takes the volume, divides it by temperature. So if you look at the experimental data, notice that temperature he uses every time he makes a division is in units of Kelvin. Don't let that bother you. So he's taking this and he's dividing it by 273 Kelvin, and he's getting a value. So for every experimental part, notice that that value doesn't vary much. So he gets an expression. So what is it that I want you guys to know about Charles' law? I want you guys to know that according to Charles' law, volume divided by temperature must be equal to a constant. That's Charles' law. First, you gotta know what he studied, volume versus temperature. I mean, which variables he used to study the gases. That's what I mean. Okay? And then you gotta know the expression. And anything that's equal to a constant, I could also rewrite it as V1 over T1 is equal to a V2 over T2. That's another way of expressing it, which means the volume in the first condition and with that temperature must always be equal to the volume divided by the temperature in another condition. If I'm not varying the moles and pressure, that should hold true for ideal gas laws. And what makes it ideal gas for gases? First of all, the size of the container has to be much larger than the amount of space the gases hold. Oh, I forgot to tell you what other assumptions we have for gases that are ideal. Another assumption for gases that are ideal gas is the fact that there are no intermolecular forces for ideal cases. Intermolecular forces tells us how the particles attract to each other or repel even. I like to call it as talking. So if it was a real case for a gas, I would at least stop by and say hi, so there's some kind of a force there. But for ideal cases, we're going to assume that everything is moving around and there's no forces. So I'm not going to say hi anymore. I'm just going to move. We're going to move by each other, collide, this and that, but there is no attracting or repelling forces. That's the second assumption we make for ideal cases. You don't have to write that down on an exam, but I want you guys to have that. And the third assumption for ideal gas laws is the fact that all the collisions are going to be perfectly elastic. What that means is that the kinetic energy is going to be conserved. When we collide, all the energy that I give you, you're only going to use it for movement. That's perfectly elastic collision. That's the third assumption. Kind of like those bumper cars. Like in a real situation, guys, when a collision happens, right, some of the energy could be used to break something. That's not perfectly elastic. But if I use all the energy just for movement, which means kinetic energy is conserved, then it's an ideal situation. So we're going to assume that when the gases collide with each other, guys, none of the gases are going to collide to break bonds and so on. Right? It's only collisions where energy is being transferred for movement, and that was the third assumption we had to make for ideal gases. Sorry if I'm coming back to that. So with a little commercial break with the assumptions we have to make, now we're going to come back to the different types of laws. So what did Charles' law study? Volume versus temperature. Go ahead, Asha.
So if when temperature decreases, volume decreases, does that mean that pressure increases?
No. In this case, the pressure is maintained because as the temperature decreases and the volume decreases, when the temperature decreases, the force is going to be less because we're slowing down. And so I shrink the volume so I can shrink the area. So now there's less force, less area, and the ratio, is going to maintain the pressure. Or in the case of the balloon, the pressure from inside and the outside has to be maintained, for it to come to an equilibrium eventually. So with Charles' law, we could talk a little more about how he set up the experiment. That's a very good question, but it comes down to, do you know which variables he studied? And he studies only volume versus temperature, so moles and pressure are maintained. How do we maintain the pressure? We'll talk a little more about individually if you experimentally speak. But that's a good question. What's the third law that I want you guys to know? A Manton's law. A Manton's law. He comes into the picture and he says, okay, let me take other two variables. We're going to take now pressure versus temperature, given that the moles and the volume of the container is not changing. He's going to study now pressure versus temperature. Let's first check and see what our intuition tells us. What's going to happen if I tweak these variables, yeah? And I'll ask you, guys, in this case, the volume is constant. You could think of it as a still container that holds some gas. Not like a balloon, the volume is subject to change, right? But for a steel container, I could say that the volume is constant. And so if the volume is constant, and there is no leak, so no gas is going in and out, we're all in the container. If I increase the temperature, what would you tell me about the pressure? According to our intuition. Guys, the size of the container is not going to be changing. The volume is constant. If I crank up the temperature, what does that have? What does that do? There's going to be more movement. And we're going to collide a lot more with the wall, so that increases what, guys? The pressure. And so there is a direct relationship between temperature and pressure, and Manton observes that in his experimental data. And long story short, every time he takes pressure and he divides it by the temperature in his experimental data, and that's what he does. And notice that before you do any divisions, you have to make sure that if it's in units of Celsius, you change it to units of what, guys? Kelvin. And so P over T is going to give us a constant. That's what we get. Oh, that's a Manton's law. Now is that to bring it up. You'll see it on some of the sample exam questions too. Or, whose law is Charles' law? And I have choices. P times V is equal to a constant, or V times T is equal to a constant. V over T V over T equals to a constant represents whose law? That's Charles' law. First you gotta check, okay, Charles started volume versus temperature. Or I could just tell you, P over T is equal to a constant, whose law is that? And I'll give you all these names. And some could be just weird names that wouldn't, have anything to do, like Graham's law or Morse's law. Like we didn't study any of those laws. So far we have Boyle's law. He studied volume versus pressure. Charles' law. He studies volume versus temperature. Amanton's law. He studies pressure versus temperature. And he concludes in his experimental data that P1 over T1 must be equal to a P2 over T2. It's just another way of saying P over T must be equal to a constant. Are we clear on this? Two variables at a time. And we get to our fourth law that I want you guys to know. Okay, these are multiple choice questions that I like to bring up or fill in the blank. What does your intuition tell you about how the two variables relate? Guys, we can't think about everything kind of. So if I don't look at two variables at a time to study gases, it's going to be confusing. It's hard for us to tell what's going on with our intuition. And so we study two variables at a time. So and I keep the other two not varying, constant to study that. So what did Avogadro study? That's the fourth law. There goes the fourth law, which is Avogadro's stuff. This was his work, guys. His work was with ideal gases and statistical mechanics too. And this is where he kind of comes up with the Avogadro's numbers. So it's not like his work was meaningful in this study, guys. And he comes into the picture and he says, okay, Boyle studied volume versus pressure. Charles studied volume versus temperature. Amanton studied pressure versus temperature. I'm going to study volume versus mole. Okay. And as far as our intuition, by the way, volume versus moles, given that the temperature is not varying, is constant. And given that the pressure is maintained, it's constant. I just want to know, what happens if I change or tweak the amount of gas? What should happen to the volume? To see the behavior of gases, yeah? And let's think about this, guys. So, okay, so let's say you have a balloon and you put more gas in the balloon. What would you expect for the volume? And the outside temperature is not changing. The pressure is maintained with the atmosphere, this and that. So if you put more gas into a balloon, what should happen to the volume? It should increase. That's what my intuition tells me, or my experience so far. You have a ball and you put more gas in it, or if you put more gas into your tire, it expands the tire, right? Now the outside temperature is maintained, so the temperature is not varying, and the pressure is maintained. Actually, there's a little bit of pressure increase, but let's pretend pressure is maintained. So we have experimental setups here. So it sets up the experiment, and we'll take a look at the data, and it formulates it for us. Every time the volume goes up, guys, every time the amount of gas goes up, the volume should be increasing. Okay, it's kind of weird the way it's put in here. So it comes down to an expression, V over N is equal to a constant. I'm just going to write constant this way. And a lot of times, guys, I'll use a symbol, a little k for the constant. And you'll see that come up in some of the multiple choice questions. And you don't need a Scantron for my multiple choice questions. I still want you guys to put your thought process. I want you guys to, intuitively tell me how these things could vary with each other. This is why we talked a great deal about what these variables mean for us. I'll say it again. So another way of saying this is just in case the phone says that it's not understood, so I have to say it again. Another way of putting it together, guys, is V1 over T1 is equal to a V2 over T2. What the heck? Whose law is that? Whose law did I just put by accident, guys? Charles' law. I apologize. V1 over N1 is equal to a V2 over N2. Thank you, Alex. Okay.
This is assuming the gas doesn't compress, right?
Yeah, assuming that the gas doesn't. I'm trying to understand that as far as compressing of the gas, right? Compressing of the gas is just done by decreasing the volume. right? So if I want to maintain the pressure, then some of the gas better leak for this situation. Okay. So we could talk. So we're going to try to keep it 2 variables at a time, but experimentally how it works out, or we got a little more to talk. But we have a very little amount of time, so I want to get to basically some of the problem solving. Fair enough, guys? So if you want to talk a little bit more with experimental details, we'll see. In fact, we had an experiment we did with ideal gas laws, but it was setting up a certain condition for us. We'll get there. These are the 4 laws that I want you guys to know. And so what I'm going to do now, before we get to the problem solving, is I'm going to put this all together. By the way, let me remind you, you got to know the 4 laws and their expressions associated with it. First, you got to know what they're starting. What we're going to do now, guys, is we're going to put them all together. Did you guys ever see that equation, PV equals nRT? Yes. In high school chemistry or in another chemistry course? Was that derived for you? Do you know where it's all coming from? It comes from these 4 studies we did. And so let me put it all together for you. So you guys know how it comes together, guys. This PV equals nRT. A lot of times, we don't have the time, so we say, okay, ideal gases, they're going to behave according to this relationship. But that relationship, guys, we build it up from these studies we have. This is why I spend this time studying, what ideal gases to this variable. Okay, studying the laws that study the ideal gases to this variable. So let me ask you, just to summarize, what did Boyle's law study? Tavan, what did Boyle's law study?
Boyle's law was P times V is constant.
Volume versus pressure, yeah? So, according to Boyle's law, P times V is equal to a constant. Good. Can I ask you, Ida, what did Charles' law study? Volume and temperature. Right? And he said that V over T is equal to a constant. Can I put them all together? Is that okay, guys? So he's going to say V over T is equal to a constant. What about Amanton's law? Amanton studied pressure versus temperature. So I'm going to say P over T represents a constant. What about Avogadro's law? Volume versus mole. So V over N is equal to a constant. So P times V over NT, guys, must be equal to a constant. And we're going to call this constant as the universal gas constant. Oh, there's a value associated with it. And I'll bring that up. And it's through these studies, when I put them all together, guys, we're going to get the equations we're going to end up using for our practice with the problem. And so I'm going to now put together a couple of equations for you, derive one of them, and give the expression for the other ones. Now, these equations, guys, if you use it with the right context, it saves so much trouble with solving the problem. So let me put all the cards on the table of what kind of equations we need, and some information about certain conditions we get in ideal gas laws. But when it comes to the problem solving, guys, realizing what equation we could use for a given problem makes a big difference in easily solving the problems with ideal gas laws. Yes, there's going to be a little bit of stoichiometry involved. There's going to be some factors involved, but it makes it so much easier to work with these problems if you have the right equation to use. The first equation I want to bring to your attention is this. If I rearrange these, multiply the T and to the other side, so if I cross it to the other side of the equality, we get this equation we've seen before. PV equals nRT. Our boxes, this is one equation that I want you guys to know. And under what context do I use this? We're going to see that in our problem solving. So I'm going to give you guys some direction eventually with the problem solving involved here. Then I expect that you guys over the weekend work with these problems before we meet again next week. And when we meet again next week, we're going to beat up more problems. I'll even project some of my past questions, some of the evil ones. But I want you guys to give it a try according to the equations, but I'll give you some direction before we go into the weekend. A good weekend, a nice weekend, and I hope you have a good Thanksgiving as well. A long weekend is being waited for. But at the same time, I want to know, I want to make sure that you guys know what to expect eventually with this study. So PV equals nRT, you got this R constant, and I'll provide you with that R constant. There's two values associated with it. One of them is going to be given as 0.08206, and the units are important to account for. This is atmospheres times liters over moles and Kelvin. By the way, whenever you work with temperature in ideal gas laws, better be in units of Kelvin. I'm going to keep emphasizing this. In our problem solving, I'm going to bring it up also. Because if you don't keep it in units of Kelvin, you might plug in a negative temperature of Celsius here, and if you plug in a negative temperature, you might get negative volume, and there is no such thing as you either have space or you don't. So you got to make sure to make things physical and true in our equations, you got to make sure that the units of temperature are what? Kelvin. But what about the units of pressure and volume? Guys, if you are specifically working with PV equals nRT, then R tells you what kind of units you're dealing with. What's the units for pressure in our R constant? Atmospheres. So I better plug in atmospheres here to match the units. What about the units of volume? It's in liters. I better plug in liters here. So when we work with a lot of times, guys, the problems are plug and chug as well. But it's not going to be as easy as that. I like to build things up, but I'll bring it to your attention. So one thing that I want to make sure we have, and what I make a mistake on is the way we work with the units. And the R decides. If you're working with PV equals nRT, R decides the units for it. And we have another R constant. For example, the other R constant that you should expect is this 62.4. And that's given in units of millimeters Hg times liters over moles and Kelvin. And so if I decide to use this R constant, my pressure better be in what units plugged into this equation, guys. I'm now talking plug and chug when we start using this equation. Better be in millimeters mercury. Of course, unless we practice, we're not going to go through the ins and outs here. It's one thing to realize, okay, yeah, I see, but when you do it, guys, it's easy to make these errors, trust me. Especially if you make, guys, if you make an error with temperature units, I don't know, I just over time, I'm becoming more and more angry about that. I don't know what. Oh, by the way, I saw a few students make a double bond on wood flooring. I had 3 cases. It happens. So it proves that our focus has to be there and just a little practice with this. And it's the same idea with ideal gases. Do not plug in units of Celsius into this equation. You gotta be in units of Kelvin. Is there another expression we're going to be dealing with? Another way of portraying these guys, and for certain problems, using the equation that I'm going to write down on the board makes it so much easier. This is called the conditional equation, which says, oh, if PV over NT is equal to a constant, I could also present that as P1 V1 over N1 T1 is equal to a P2 V2 over N2 T2. So all the pressure, volume, moles, and temperature in one condition must be equal to the pressure, volume, moles, and temperature in another condition. And I like this equation. And I'll show you before the day ends. If you remember this equation, you could also basically derive all the expressions for all the laws we talked about, as long as you remember what the laws started. For example, if you are dealing with Boyle's law, what did Boyle study? P and V. And so if I just keep the pressure and the volume in this equation and erase everything else, aren't you going to get P1 V1 equals P2 V2? I'll bring this up in our problem solving. So it's an equation worth knowing. And for certain questions, if there is a change going on with any of the variables, if I read a question and it says, oh, my temperature starts at 25 Celsius, but I'm dropping it to 0 Celsius. Oh, that's a before and after condition. Then I know I'm going to use this equation. And if I use PV equals nRT, guys, it makes it so much difficult. I mean, you can get away with it with some algebra, but why make it complicated? This is why I'm deriving these equations to bring it to a point where you could use the correct equation for the radical, the problems, and makes it so much easier. But we got to do this with an understanding. I like this equation for certain problems. And the nice thing about this equation, guys, is I don't have to be confined with certain units of pressure. For example, I could give you pascals for P1, and as long as P2 is in units of pascals, then I could plug in any units of pressure I want, as long as they're both the same. So R doesn't decide anymore in this equation what's going to be the units of pressure or volume, as long as they're consistent. But with temperature, guys, please do not use Celsius, even if T1 and T2 are Celsius. And I have this brought up in our problem solving, just so we could see some of the possible errors we could make and to fix it. Yes, no, how?
Are we never going to use kilopascals in the
Yeah.
constants?
Not the R constant.
No.
These are the only two R constants I expect. And if I want you guys to do a conversion, then I'll give you the equalities for it, of course. If I ever want you guys to convert from one unit of pressure to the other, then I'll give you guys the equalities for it. But sometimes I don't. I'll give you kilopascals and I don't. Maybe it's conditional and you don't need to change it to atmospheres or millimeters mercury, right? And so we gotta be careful about this. We've started this in our Chem one time. Just the way we're starting here. And it's the same ideas. But I'm gonna add one more equation, which is derived for it. I don't know if we have too much time to derive it. The other equation, guys, that comes up is about bringing in the molarity and density into the picture. Because sometimes we're dealing with unknown gases and we want to be able to find out the molar mass for it. Not molarity, I'm sorry, the molar mass. So if you take PV equals nRT, so for PV equals nRT, I want to replace volume and moles in terms of molar mass and density. How would I do that? Guys, again, this third equation I'm going to give you saves a lot of time for certain questions, which has to do with density and molar mass. It also gives us a relationship between density and molar mass. And I have questions that come up here that I want you guys to study. So one thing that I want to derive this for you. You're not responsible to derive it on an exam. But density, what was density, by the way? It's mass over volume. And what would you say about molar mass? How would I find molar mass, guys? Yes, we get it from a formula that's given to us, right? But molar mass could be also found if I take the mass and divide it by the moles associated with that mass. So mass over moles, wouldn't that give me information about molar mass? Oh, grams per mole. And if I have these expressions, then I could I could rewrite V in terms of density. Can I do the algebra and write down that volume is equal to mass over density? Can I do that? So I'm crossing the volume there and bringing the density down. You guys want to know how I do my algebra? We could talk. And then I have, in this case, I could rewrite moles in terms of mass over molar mass. And I'm just going to replace that instead of volume and the moles. I'm going to replace volume and the moles in terms of these other variables. So now it becomes pressure times, my volume is the volume is going to be M over density, and my moles, I could rewrite it as mass over molar mass times the RT. And in here, the masses cancel, and so we get a 1 here. Sorry for your notes. And if I cross, because I don't want to have it divided, so if I cross the density here and I multiply everything by molar mass, I get this other expression, which says pressure times molar mass must be equal to density times R and T. And the density better have units of liters in here, because R is in units of liters. And so there goes another equation that's worth knowing. Why? Because it shows how molar mass and density of the gases are directly related to each other for ideal cases. And we're talking gases. Everything we have on the board, guys, is about ideal gases. No intermolecular forces. This doesn't work for liquids. One last thing that I want to put on the table before we get to the problem solving. And it's about this STP condition. It's called standard temperature and pressure. That's another thing that I want you guys to know. Standard temperature and pressure, by the way, it gives us a certain value. I mean, we don't have to know why we pick this temperature and the pressure values beyond this class. Why do we pick this as the standard for us? So we could do things with respect to that. There's ideas involved with that, which is beyond the class. If you're asking that question, that's a great question. But guys, let's just get to know what those temperatures and pressure values are. So when I give you an STP, that just is supposed to, and you have to know this, it's supposed to represent a pressure and a temperature value, and the pressure at STP is 1 atmosphere, or it's 760 mmHg, and you gotta know that. Sometimes it comes up in the problems, and you gotta know what the pressure is at an STP. You're gonna see now a problem solving come up many times. The temperature at STP is 0 Celsius. Why 0? Not the question, guys, here. We shouldn't go with that. But you just gotta know that it's 0, but I can't keep it as a 0 Celsius, so it's another way of saying it's 273 Kelvin. And you can just keep it as 273. Now, you don't have to go, extra decimal places. That's STP. It stands for standard temperature and pressure. And I got values for those. Agreed? But there is a little more at standard temperature and pressure. We did a lab for confirming that. It's called the molar volume. And it turns out that if I plot this temperature and pressure, you guys could give this a try at home to prove this to yourself. If you plug it into the PV equals nRT and then pick a value for moles, you also get an equality at STP, which could be useful for certain problems for us. And the equality says for every 1 mole of an ideal gas at standard temperature and pressure, I should be getting 22.4 liters for the volume. So let me ask you, at standard temperature and pressure, is your volume 22.4 liters? The volume, can it be 22.4? Does it have to be 22.4 liters? No. It's a common misconception, guys. That was, again, I always say this and it seems harsh. No, it's not 22.4 liters. What you should be clear about is that it's gonna be 22.4 liters if I have 1 more. It's an equality that we're dealing with. Okay, that meant an equality here. So if you tell me for 1 mole of a gas in an ideal situation, we have 22.4 liters for an ideal gas, then that's a true statement. But I can't just say, oh, my volume is 22.4 liters. No, it's not. It's only 22.4 liters if I have 1 mole, right? Is that clear? At STP, I could surely say that the pressure has got to be this and the temperature has got to be that. This is why we have an STP. But when it comes to volume or moles, guys, we have to have it as an equality. This equality is going to help us solve problems without even using the equations, as long as things are at STP. And I have those kind of variations for your practice. So let me project now, before the lecture ends, the kind of questions that I expect from you. I have a whole bunch of them for practice with all the answers there, but just to talk about the approach. So I presented the equation, so how do we approach these over the weekend? And then when we meet on Monday, guys, I want you guys to start working on this, but when we meet on Monday, we're going to beat up some of these problems. I'm going to pick the ones that is, like each question is going to teach us something. So let's take a look at question number 1. If you allow me a little more time, I would like to kind of give this a start and tell you how you can solve this. Okay, so the question says you have this balloon, and the volume is given to me, 785 milliliters at 21 Celsius, and they're saying that the temperature drops now to 0 Celsius. And they don't say anything about the moles, and by the way, if the problem says nothing about the moles, if the moles are not varying, then it's constant. Now, if I mention in the problem that, oh, there's gas leaking, then the moles will change. But if I don't say anything about any gas leaking or going into the container, then we assume that is constant. Remember, I was an undergrad, it's like I read the problems, like, they didn't say anything about the moles. If they don't say anything about the moles, it's a constant. Assume that it's a constant. Are we okay with it? But if they do talk about, they don't have to use the word moles, all this gas being lost or gained into the container, then it's not a constant. So what's the first step in this problem? The first step is to write down what you got. And in this question, are any of the variables changing? This is the highlight that I want to make. Is there anything that starts with one value and ends up with a different? Yeah, temperature is. In fact, maybe the volume is changing too. Should be. Guys, I call this conditional problems. And so when you say it, if you have a certain temperature you start with and you end up with a different temperature, what kind of a question is that? Conditional. And do not use PV equals nRT for a conditional problem. You'll be stuck. You could get away with it. I could show you, but why do extra algebra? And this is why I brought this for, different equations on the board. These different equations that I have on the board, guys, is to prove to us that for a given question, using the right equation saves a lot of time. So in the homework, for question number 1, when you read this question, the question says that the temperature is changing. If you read any question and you have a hint of, oh, there's something varying, there is condition 1 and condition 2 now. Do you see what I mean? And if it's conditional, guys, what's the best equation to use? P1 V1 over N1 T1 is equal to a P2 V2 over N2 T2. Guys, I'm reading this question. The question tells me that you start with 21 Celsius and then you end up with 0. And they don't say anything about pressure. They don't say anything about moles. If you use PV equals nRT, now you're going to have to, where is the moles in it then? Where is the pressure? So you have to come up with it. So it's better to start with the right equation, because if you start with this equation, you know what's the nice thing about this equation? Whatever is a constant, whatever is not varying, then it drops out. The moles, whatever it is, it's the same. So can you cancel that? What else is the same? The problem told me that the pressure is the same, right? Can I cancel that also? And whose law is that, by the way? Charles. That's why I like this universal, when I put everything together, I like this equation, because in this equation, if you get rid of whatever is not varying and just stay with the variables that do go through a change, then you would know what kind of a law you're dealing with. So that's Charles' law. And in this question, guys, all I have to do now is just do what? Plug in Charles. And make sure you don't keep your temperatures, guys, even though they give it to you in Celsius, make sure it's in Kelvin. And so if I plug in the volume 1, which is 785, and it's milliliters, and I plug in my temperature 1, which is 21 Celsius, 294 Kelvin, make sure you keep your temperatures in units of Kelvin. And this is 73 Kelvin. Can you now solve for V2? Everything is already solved for us. What I want you guys to practice, and there's some variations that are going to teach us something. So go through it. Don't just look at it and say, okay, yeah, I see what he's saying. Go through it, because just in case you make a mistake with not changing the units to Kelvin, I want you guys to experience that beforehand. That's our practice. And there's certain things that come up. There's certain variations that I know is going to teach us something. But you see, using the right equation saves a lot of time. Don't use PV equals nRT. When would you know you're using PV equals nRT? If the problem doesn't mention anything changing. And I want you guys to get that sense. So, the approach should be, is it conditional or not? You got to check that first. Okay. Are we talking density or molar mass? So we can pick the right equation. It saves a lot of time. Monday we're going to do problem solving, guys. I'll post this video as well. Thank you very much for this one. Thank you for the video. I appreciate it. And now the whole memory is gone.